Okay, welcome everybody to the periodical Netpore webinars. As you can see, I'm not Frederic Cunen. She's currently traveling in the US. So my name is Luca Boarino. I'm working at INRIM, the Meteorological Institute of Italy. And I have the pleasure to present the first speaker of the webinar. Obviously, this webinar are about half an hour, let's say 20, 25 minutes plus questions. And we generally have two speakers. So the first speaker is Jan-Henrik Smat. He's the leader of the nanostructured metal oxide research group at the Laboratory of Molecular Science and Engineering at the Åbo Academy University in Turku, Finland. And the focus of the group lies on the design of novel nanostructured material, nanostructured metal oxide materials using solution processing for applications in solar cells, molecular separation, and functional coatings. So please.
Thank you very much for the kind introduction. And I'm, of course, very grateful to be able to present some of these topics that we have been working on, especially in this forum on these porous semiconductors. I hope that you have many questions, and feel free also to contact me afterwards if something comes up that you want to discuss more. As the title suggests here, I will give a brief overview of the solution processing of various metal oxide materials and that we have been working on in my group. And after this, I will also give a recent examples of where we can utilize these materials, for instance, in molecular separation and in solar cells. However, before we get into this science part, many of you may not have heard about Åbo Academy University. You might have noticed, you might know where the city of Turku is located in Finland in the southwest. And you also probably know Jarno Salonen, who is then a professor at the University of Turku. So actually, Åbo, in the name here, it means Turku in Swedish. So it's the Swedish-speaking university in Finland. It's the only one, actually. And the good thing here is that we have now a new chemistry building, and it's actually a joint building together with the University of Turku. So we hope to have a lot of interesting collaborations between the two universities here. So at Åbo Academy University, we have 4 different research profile areas. And one of them is these technologies for a sustainable future, which my group is belonging to. And as you can see from here, one of the main goal is then to replace fossil raw materials with renewable resources, and also a lot of focus is on solar energy. And within this research profile, there's a lot of collaboration between different groups. And for instance, I'm working quite a lot together with the physicists on solar cells. So I provide the materials, and they are looking then in how they are operating. There's also another research profile area in solutions for health. So of course, my research is also a bit leaning towards that in some cases. But here is a brief outline of the focuses of my research group. So the name of the group is Nanostructured Metal Oxides Group, but I usually make it short, like nanoxides. So the idea here is to design functional metal oxides, so we can make, for instance, bulk materials or monoliths, microspheres, thin films, core shell structures, and other types of functional coatings. But the main methods are usually then solution processable, so no kind of complicated machinery is needed. And the application areas are, of course, in different types of molecular separation, gas sensing, and also in solar cells we have been working quite a lot with. But of course, if you have some ideas for a collaboration based on this presentation, feel free to comment on that. There's, of course, many other applications that they can be used for. So let's start from the beginning. And if you want to make some kind of nanostructured metal oxides, it's really vital to understand this sol gel processing. And basically, by changing here the properties of the sols that we are using, we can tune what kind of morphologies that we end up with here. So this is an example of silica. And by using then different pH, like low pH, we can end up with bulk gels, and high pH, we end up with nanoparticles. But there's many ways we can tune these sols. Another way to control the morphology is to tune the processing methods. So for instance, we can use dip coating to produce thin films. We can use fiber spinning to produce fibers, and so on. But the good thing here with sol gel chemistry is that it's also quite easy to make some kind of porous structures. I think many of the groups in this Netpore make some sort of mesoporous silica that is used then for controlled drug delivery and such as this kind of thing. So using for instance, surfactants or block copolymer micelles then to make these kind of porous structures. We can also use this, for instance, evaporation-induced self-assembly to create porous thin films, silica titania, for instance. But another way also to produce porous structure is, for instance, to use this polymer-induced phase separation in kind of bulk gels. And you see here the scale bar here is like 50 micrometers. So these are pores then on a much larger scale. And basically, we have used this to make micropores in silica monoliths and also in larger pore structure in titania thin films. And this can be done by adding small amounts of polymers, for instance, and that creates this phase separation in the structure. But as I mentioned, these are quite easy then if we have metal oxides like silica, zirconia, titania, and these kind of things. But when we want to make something more exotic like iron oxide, cobalt oxide, nickel oxide, and so on, then it becomes much more tricky to use this sol gel approach. And basically, we have to use something else. And we have been focusing quite a lot on this nanocasting approach, is basically to use some kind of template to replicate this kind of structure into something else. So we can also think about this casting at the millimeter length scale, like you know how to make tin soldiers. You melt this tin metal and then it solidifies, and then you remove the mold and you get this kind of replica of the mold. So in the same way, we can also use a mesoporous silica, for instance. We are filling these pores with some salt solution, for instance, and we are using some thermal treatments, for instance, to convert it to a metal oxide. Then we can remove the template or the mold by, for instance, leaching in sodium hydroxide, for instance, to get up. And then we end up with this negative replica of the starting material. So what we have been focusing on is also to not only replicate the pore structure, but also the morphology. And this is something that we have been working on quite a long time ago. But so for instance, here we have these monoliths that we can replicate. There's a lot of different compositions that we can make. Microspheres, they are also quite easy to replicate in this sense. And also these thin films we have been looking at into different metal oxides. Also carbon structures we can make this way. So why are we interested in these hierarchically structures? I think it's very important that, for instance, this in many applications, we need to have a combination of let's say, small pores that can then facilitate the reaction that we are interested in, and also to have larger pores so we can have material transport through the material. So of course, molecular separation, catalysis, sensing, and renewable energy application, this is very important. So in this example, this is a hierarchically structured silica monolith. So we can control it on 4 different length scales at the same time. So these 2 types of mesopores give rise then to a high surface area, while these larger macropores then facilitates this material transport through the sample. And finally, we can also have control the bulk morphology. So we can, in this sense, we can also tune the for certain application we can make it. At the same time, we can also use these microbeads, microspheres. We can pack it into a column, for instance, and in this way we also have a hierarchical pore structure, basically. So actually, the voids between these spheres is also giving rise to some kind of larger pores in a sense. This is of course nothing new. This is commonly used in HPLC columns, for instance, but we can also think about other applications where this gas flow is important. So I will give one example of this, and we have been working a bit. We have collaborated with a group at the University of Helsinki on this in-tube extraction, or ITEX method. So the idea here was to use some sort of micrometer-sized silica zinc oxide composite material, and to analyze here different types of nitrogen-containing compounds from air samples, basically. So here the idea is that these should absorb these compounds, and then we can then desorb them and analyze them later on. So this ITEX then it allows them for a continuous and long-term sampling, basically. And as I mentioned, we have to desorb it and then use GSMS determination then to analyze what kind of gases are, for instance, in cigarette smoke or something like that. So the group in Helsinki, they had an earlier study where they found out that zinc oxide is very good material. It's very selective for amines. But the problem with their particles was when they packed it into the column, it was very difficult for the air to flow through that because they were packing very closely. So we discussed this and we came with a solution. We need larger particles. And so our strategy was here then to make a composite material. So we would first make 5 micrometer porous silica materials. The idea here was that they should have this MCM41 type structure, which means that it's like CTAB, acetyl trimethyl ammonium bromide templated structure. And many of you know that it's very difficult to make such large particles with ordered structure. So we had to use this pseudomorphic transformation method, meaning that we start here with commercial silica microbeads, and they have an unordered pore structure. So when you're having it at high pH, you add this CTAB and heat, then it will transform into this ordered structure. So this intermediate stage, we have this kind of structure, and then we start to infiltrate with zinc nitrate salt. We use some heating then to produce this zinc oxide. And then we repeat this a couple of times. So the final point was then to have silica with MCM41 type structure as a support, and then we have zinc oxide nanoparticles inside the pore structure here. So here are some results. You can see here the original structures. This is the morphology of the particles. This is after this pseudomorphic transformation. You can see here that we still have the particles, but there are also something smaller here, which I think is from that it has also nucleated some smaller MCM41 type structures here, but it did not affect the application later on. And here is then after adding the 2 cycles of zinc oxide. And you can see here also that after doing this pseudomorphic transformation, we go from 30 nanometer very broad pore size to a very sharp 2.75 nanometer pore size. So we have basically also here from the small angle X-ray scattering data, we can see that we have an ordered structure. It's not perfect MCM41, but it's still very, very close to that. And then after adding more of this zinc oxide, 1, 2, 3 cycles, you can see the surface area is going down, the pore volume is going on, because we are filling it up with zinc oxide. But looking at the XRD here, we can see this broad peak here is from amorphous silica. We don't see any crystalline zinc oxide before the last infiltration cycle. So it means that we have also most likely amorphous zinc oxide in this case. And this is good also because then it has a higher reactive surface, basically. So here are some results from the ITEX. You can see here that the yellow one here is the highest amount of zinc oxide, and that binds then more strongly to this amino containing compounds, while the other ones are not really bonded. We think that this has to do with the acid-base properties of zinc oxide, that it selectively then can bind to these amine compounds. We saw some problems with the flow rate for the highest zinc oxide loading. We think here that some of the particles are maybe coming off and it starts to clog the system. So in the rest of the paper, if you're interested in this, you can check it. There it was also tested with natural air, cigarette smoke, and this kind of thing. So and we could see that this is a really good material for that. Another study that we carried out was related to this phosphopeptide enrichment. This is done by something called metal oxide affinity chromatography. And basically why we are interested in phosphopeptides is because there's a lot of interesting biological reactions taking place, and these are very important for various biological studies, so to say. But the problem is that they are not very abundant, so we need to kind of enrich these before we can study them with mass spectrometry. And typically, the standard material so far is like titanium and zirconia that work very well with enriching these. But what we wanted to do was to study a broader number of materials. So we have 7 different metal oxides which we have made by this replication method. And we can see here that by the acidity of these metal oxides, or the isoelectric point, increases in this way. And we can see that the binding strength for these phosphopeptides are inverse to that. On the other hand, the selectivity towards phosphopeptides with multiple phosphorylation sites is actually going the other way. So with these materials, we can actually detect some more uncommon phosphopeptides or phosphoproteins, for instance. So I think by combining different materials, we can get a better picture of these biological events taking place in the body. So this was very short about this kind of separation part. I will now move over to the other focus area that we are working on, and this is on thin film solar cells. And we have been working on organic solar cells, where we have this organic donor acceptor system as this semiconductor material which absorbs the light. And the other hand, we have also studied a bit about these perovskite solar cells, where we have these organic, inorganic metal halide perovskites that absorbs the light. And the efficiencies of these devices are, I would say, very close to the standard silicon solar cells used today. But what I wanted to focus on is this electron transport layer. So we need this to be able to extract electrons from the device. And these are typically then, it can be organic, but what we have studied are then mainly metal oxides. So I will jump over to that part. And in most cases, we use spin coating to produce these kind of metal oxides, but spin coating is not a very good way, like larger scale. So what we wanted to do was to use this dip coating method to produce uniform compact titania films over larger areas. And we can get very nice thickness dependence here by just changing the concentration of this titania precursor that we have been using. We can also tune it by changing the withdrawal rate here. What we found out here was that we need to have a thickness about 30 to 50 nanometers in order to have good coverage. The reason here is that this FTO, this fluorine-doped tin oxide contact material, is very rough. So with the dip coating method, we are not forming a uniform layer, but it gets a bit uneven. So here you can see that we have a much better coverage of this. And this is something that we have looked for instance, in perovskite solar cells, but also organic solar cells. And in another study, we have also used this block copolymer templating to produce porosity in the film by this evaporation-induced self-assembly approach and dip coating. So simply by adding more of this block copolymer, we can increase the porosity even up to 50%. It was a bit surprising that even at this is the highest porosity sample, that the efficiency of those devices was almost the same. It did not change. So the problem would be, of course, that if we have pinholes, like small holes in the structure, that the perovskite located here would be in direct contact with this FTO glass, and that would cause short circuit. And so that's why I think this was interesting to see that this still worked. And we think that it's because the perovskite crystals are so large, so they will not penetrate through the entire system. So we'll end up this part with just showing that we can have different types of porous titania films. I mentioned already this block copolymer templating and just this nanopattern thin films, and these were this controlled phase separation, but we can You can also just use nanoparticles and make a nanoparticle structure, and you can see it's very uniform here on a glass slide. And this would also make a very cheap porous structure. So just to conclude my presentation, I just want to say that just by using a combination of salt gel processing and this nanocasting approach, we can actually design metal oxides, the nanostructure, the morphology, simply by solution processing. And it's also beneficial to have a hierarchical pore structure for molecular separation applications, because then we have a high surface area and good material transport. And for these solar cells, I would say that this dip coating method is a very good method to make solution processable large-scale deposition of these electron selective layers. And here are some of the funding for this work. And also, please don't hesitate to contact me after this if you have some ideas on collaborations. And if you have any questions now, I'm very happy to answer to that.
Okay, thank you very much for the very interesting seminar. We have time for questions. Don't be shy. I have a couple of curiosity, starting from the end. I'm not sure to have understood how you use diblock polymers as a template for titania. So you are depositing titanium by dip on the diblock polymer template already opened with a phase removed.
Yes. Sorry, I was going through it very quickly. So I think I showed it also earlier here. Can you see this slide?
Sure.
Yeah. So this is, of course, evaporation-induced self-assembly method. So typically what we have is that we have some kind of solution then with these block copolymer micelles, and we have evaporation. And during this evaporation, they will self-assemble into some ordered structure, and then you can do some thermal treatments to get rid of the template. This is now for like bulk materials, so to say, but you can imagine if this would be a dip coating sol, and then you could deposit that on a glass slide, and then it will also self-assemble into a structure like here.
So you're starting with the micelle structures, okay?
Exactly.
But maybe we can do the same with, for example, vertical cylinders and removing one phase, no? Or not? For example, I don't know, PMMA and polystyrene diblock polymers. You get the vertical cylinders. You remove one of the two phases, like for example, removing PMMA, and so you have some, let's say, holes, and you can do this in the same way or not.
I'm not familiar with it, but I think that should be possible. Yes.
Yeah, I think so. And the other question is, these techniques, how conformal can be, because MCM41 it's really small. I mean, the structure is few nanometers. So how is the surface of the metal oxide you are in some way infiltrating? Is sufficiently conformal?
No, we are talking about the this part, right?
Yeah.
Yeah. Yeah, I think here um, it's of course there we try to see this with some TEM images. I have TEM images of these samples as well. We cannot distinguish between silica and zinc oxide. So this means that the zinc oxide, if there are particles, they are very small. It might also be that it's more like a coating on top of the MCM 41 silica pores in a
Uh-huh.
way. But I think like when we are increasing the concentration of the zinc oxide, or like doing several cycles, we also start to see these zinc oxide nanoparticles, and because they are also crystalline, as you can see here
Mm-hmm.
for the last sample here. So I think this is important, because otherwise the gas would not be able to enter the pores. So what we don't want to have is of course that the pores are blocked in some way.
Yeah, it's not really easy. Eh?
Yeah,
I come from porous silicon and all the technique, and I'm also working on diblock polymers. And when you're dealing with this pores at this level, it's really difficult to infiltrate efficiently and with a good control any type of material, let's say, in this
yeah,
pores. So I think it's really challenging.
yeah. I think in this case the loading is about 10 to 20 weight percent. So it's not really a lot of zinc oxide in this case.
Mhm. Thank Thank you very
Thank
much.
you.
Other questions? I don't see raised hands. So let's thank the first speaker, and we can move to the next speaker of the day, Dinara Sobola. And a few words. She received her PhD degree in physical electronics and nanotechnology at the Department of Physics at Brno University of Technology. Currently, she works as a researcher in Central Europe Institute of Technology in the group of advanced ceramic materials. So please, Dinara, the time is for you.
So I will share my screen.
Okay,
So can you see it?
perfect. You can go.
Okay. Thank you very much for the nice introduction. It's a pleasure to contribute the network on porous semiconductors and oxides. These materials have a huge potential in water cleaning because the porosity of surface is very important for catalysis, because it's actually defines the surface area and consequently the efficiency of the catalyst. So I will shortly tell about the problem, some short review. I will tell about what we done in our lab in this field. And the problem of capacity of clean drinking water is obvious. It's a great problem all over the world. It is mostly caused by our activities, like our householding, industry, agriculture. Domestic sewage is a primary source of disease-causing microorganisms and putrescible organic substances. It presents a direct threat to public health. So domestic sewage is also a major source of plant nutrients, mainly nitrates and phosphates. Toxic water contains poisonous, radioactive, explosive substances that can also bring serious damage to health, for example, as cancer, damage to chromosomes, even be a reason of birth defects. Source of toxic chemicals include improperly disposed wastewater. It comes from industrial plants, chemical process facilities, as well as surface runoff containing pesticides used in agricultural areas or suburban lawns. Oil pollution occurs often accidentally when oil from roads and parking lots is carried in the surface runoff into the water bodies. So, among all effective methods for water treatment, today we will point out photocatalysis. Photocatalysis is based on advanced oxidation processes. It means that it relies on the generation of highly reactive and oxidizing hydroxyl radicals. Titanium dioxide is the most widely used catalyst in heterogeneous photocatalysis because of its photostability, non-toxicity, low cost, and stability under most environmental conditions. And the term heterogeneous appears here because the catalyst and the reactants are of different physical phases, like solid particles, and they're in the water. Large amount of reactive oxygen species such as hydroxyl radicals and superoxide radical anions are produced on the surface under light radiation. And these reactive radicals are regarded as the main responsible species for the degradation of the organic pollutants in the wastewater. But large band gap demands using of ultraviolet radiation for generation of charges on the surface of this titanium oxide. And the modification of titanium oxide or using of other materials with smaller band gap could help to replace ultraviolet by natural solar radiation, which is free in most areas and feasible, especially for industrial wastewater treatment. So, to overcome this problem, numerous compositions were tested as photocatalysts. We also made an attempt in this direction by preparation of one-dimensional phase-modulated structured layers of Aurelius phases. Aurelius phase structures are built from layered structural framework of perovskite-type units interlaid by bismuth units. Here we see a scheme of the processes during atomic layer deposition and subsequent annealing of the sample. We also see here the morphology of the sample before and after deposition of the bismuth ferrite upon titanium oxide. So what we got? The enhancement of the photon excitation efficiency of electrons due to the atomic layer deposition coating. So it is confirmed by observation of the difference between photocurrent in pure and iod-coated titanium dioxide. The photocurrent was measured under pulse radiation of UV and visible light, and the result of photocatalysis by methyl orange degradation also demonstrates significant potential of the synthesized structure as a photocatalyst. Issue for photocatalytic system to reach a high overall efficiency. Electron-hole recombination could significantly reduce the efficiency of converting the absorbed phonons into redox radiation. The electron-hole recombination is related to many intrinsic and extrinsic factors such as surface, interface sites, internal defects and dislocation, depletion regions, built-in electric fields, external bias, drifting velocity, and the mean-free path. In general, larger driving force and high crystal quality are favorable for achieving high charge separation efficiency. So as we saw above, tuning the band structure by doping or heteroband structure by coupling was found to be useful to improve light absorption and photoresponses. And as we can see here, the ferroelectric materials provide an additional internal electric field to drive charge transport through the semiconductor or across the surface. Polar surface terminations produce an additional field at the catalyst-water interface to enhance the photochemical activity. Ferroelectric materials refer to a category of materials that exhibit spontaneous electric polarization. Ferroelectricity was first reported by Joseph Walaszek during his research on the dielectric properties of special salt rock. And to date, more than 700 ferroelectric materials have been discovered, and the majority of them are complex oxides. These materials have been widely used in many functional devices such as sensors, dielectric capacitors, non-volatile memories, actuators, and energy harvesters. Photocatalytic water splitting typically relies on the internal electric field to achieve photogenerated charge separation. The spontaneous electric polarization of ferroelectrics could offer a strong internal electric field toward the photocatalytic water splitting process. Depending on the direction of ferroelectric polarization, it can enhance the separation of charge carriers and facilitate the water oxidation and reduction processes. Ferroelectricity also shows strong influence on the tuning of photocatalytic performance, as ferroelectric materials are able to couple with the other photoelectrode materials, providing substantial impacts on the internal electric field. So, when piezoelectric materials are stimulated by a mechanical force, the built-in polarization electric field occur, and then the specially promote charge separation during the catalysis process. It provides effective reactions with dissolved oxygen molecules and water to form active groups for decomposition of organic pollutants. Some of these materials have a certain degree of photocatalytic performance too, but especially the synergetic effect of the piezoelectric and photocatalytic performance greatly increases the degradation efficiency of pollutants through the generated internal electric field under external force. It helps to effectively inhibit the recombination of generated carriers. So the oscillation is required to restore the electric field during the piezocatalytic process. It's worth noting that continuous ultrasonic vibration will not only cause piezoelectric effects in piezoelectric materials, but also bring about sonochemical effect. A sonochemical effect possesses the characteristics of low implementation cost and environmental friendliness for the degradation of organic and unorganic pollutants in water. It is well known that low-frequency ultrasound generally causes transient cavitation. These these bubbles generates in transition cavitation quickly grow, and they grow to the critical point, and then they burst and induce some hydrodynamic phenomena such as shear forces, stock waves, for example, or high velocity microjets, which can easily destroy walls of the cells of, for example, pathogenic organism, or destroy the polymer chains of some pollutants. The piezocatalysis and sonocatalysis simultaneously emerge in the in situ ultrasound-induced piezoelectric catalysis process, as shown in this slide. This type of smart materials can utilize natural and available sources of noise, stray vibrations, mechanical waves, for example, in the sea, which will improve their cleaning potential. We checked this concept by active membrane based on polyvinylidene fluoride nanofibers with magnetite nanoparticles, which we incorporated inside of them. The samples were synthesized by electrospinning, so you can see it here. We choose these materials because hematite is a well-known narrow bandgap photocatalyst with a number of advanced properties, which are listed here. Among organic ferroelectric polymer like PVDF is an ideal candidate as a piezoelectric catalyst due to its high piezoelectric coefficient. From a practical point of view, it is also very important that flexible ferroelectric material it's very sensitive to vibrations, and this flexibility another advantage to these membranes. So PVDF is known to have at least 4 crystalline phases, alpha, beta, gamma, and delta, due to the parallel molecular packaging of beta, gamma, and delta crystalline phases. They are more polar, and they are considered to be ferroelectrics. 10 weight% of magnetite nanopowder was added inside the polymer solution, and we provide the electrospinning as was performed at previous slide. Here we see a focused ion beam cut in the middle of the sample, which shows a large amount of the voids inside the mats. PVDF is formed in the form of elongated fibers of various diameter with preferred orientation. An analysis of the distribution of nanofiber diameters was performed by ImageJ program. We found that the average diameter was 170 nanometers. Elemental mapping for the site showed that these elements distributed quite homogeneously. We also check the composition of the membrane by Fourier transform infrared spectroscopy, Raman spectroscopy, X-ray diffraction. So we can conclude that polyvinylidene fluoride nanofibers are mainly in the most electroactive beta phase, and powder inside the fibers has a hexagonal structure of hematite. In order to check the piezoelectric activity of the individual nanofibers, we used piezo response force microscopy, and the basic idea of PFM is to affect locally the piezoelectric sample. We check the surface by the electric field to analyze the resultant displacement on the sample surface. The PFM technique is based on the converse piezoelectric effect, which is linear coupling between the electric and mechanical properties of the materials. Since all ferroelectrics exhibit piezoelectricity, an electric field applied to a ferroelectric sample results in changes of its dimension. To detect the polarization orientation, the AFM, atomic force microscopy tip, is used as a top electrode, and it is moved over the surface. So the melting endotherms were measured at the membranes, and they show that the melting point obviously increases due to presence of hematite nanoparticles. We know that the melting point of electroactive phases is higher due to the fact that all transconformation forms more compact. We can conclude that hematite nanoparticles act as nucleating agents for polyvinylidene fluoride, and they intensify its crystallization. So, to confirm the hypothesis of the interfacial interaction between the filler and the polymer, a study was carried out using X-ray photoelectron spectroscopy. Figures show that XPS images of clean and hematite-containing fibers contains the elements which we expected. Then, for a semi-quantitative interpretation of the data, it was necessary to calculate the integral areas of each component. And it can be seen that the addition of nanoparticles led to the decrease in the content of at the surface of carbon fluoride groups. This is actually in good agreement with the Fourier transform infrared data, which was shown that the addition of the nanoparticles led to an increase in fraction of electroactive phase in polyvinylidene fluoride. And it is also possible to understand that polarization and reorientation occurs during the interfacial interaction between the iron oxide nanoparticles with polyvinylidene fluoride. From the lowest figures, we can see that magnetite nanoparticles provide a change in density of electronic state even without irradiation. With piezophotocatalysis, this effect can be enhanced, which can reduce the activation barrier for ongoing chemical reactions. So here we see the results of piezocatalytic and piezophotocatalytic experiments on the oxidation of industrial dye. We used methylene blue under irradiation of ultraviolet and visible light and only visible light. We see the curves of piezophotocatalytic decomposition of methylene blue under simultaneous irradiation with light and ultrasound processes. The photodegradation efficiency was 99.5% within 60 minutes. So in similar experiment during 1 hour, only without light radiation, it was only piezocatalysis, the degradation was decreased by 30%. Also, under similar condition, efficiency of decomposition was investigated in the process of sonolysis, which is ultrasound treatment without catalyst, and photolysis, which is right irradiation also without catalyst. Then we check the reusability and durability of hematite containing PVDF fibers. So we evaluated it during 5-cycle piezophotocatalytic experiments. The data are depicted in the graph and show that after 5 cycles of reuse, the efficiency of piezophotocatalytic decomposition decreases only by 10%. The X-ray diffraction spectra show the pattern of hematite containing PVDF nanofibers before and after these 5 cycles of piezophotocatalysis, and it can be seen that the crystal structure of material does not change, which indicates the stability and chemical resistance of the catalyst. So in this figure, we can see the schematic representation and explanation of the photocatalytic charge separation mechanism from the chemical point of view. This acceleration is due to the fact that the piezo potential affects the piezo photocatalytic process. Piezopolarized charges from a piezoelectric effect cause band bending at the interface, promoting special separation of the photogenerating carriers, and thereby it limiting recombination in the hematite particles. In this case, the cavitation pressure caused by action of ultrasound on the PVDF nanofibers due to the piezoelectric effect continuously generate an internal alternative electric field. Due to this, there is no electrostatic screening of the interface and the piezo potential is not saturated with free carriers. Free charges accumulated on the surface. They have strong redox properties and can react with molecules in the solution, in particular with water and with oxygen. The data obtained on the capture of active redox forms are very difficult to interpret, even to some extent there are some extent contradictory, which proves the complexity of the ongoing physicochemical processes. For piezocatalysis, it was shown that the decomposition of methylene blue is significantly inhibited when isopropyl alcohol is added as a trap of hydroxyl radicals. This suggests that hydroxyl radicals are the main component for decomposition process. But we should note that hydroxyl radicals can be formed in the system also due to reduction or dissolved oxygen by piezo-induced electrons and the oxidation of the absorbed water by piezo-induced holes. So the next idea is using of magnetic field, and within this idea, the magnetic reactive catalytic nanomaterials are localized in the specific zone of a magnetic field where chemical reactions are allowed to occur. Magnetic field simulation, as indicated in this figure, could be done by change of magnetic force. Magnetic particles of magnetic material will answer to the stimulations by movement and by heating. The concept of heating magnetic nanoparticles, which can be delivered in certain place, are in the center of interest for various treatment procedures, for example, for treatment cancer. And the development of these materials with magnetic properties that can be easily removed after application of external magnetic field after making photocatalysis. So it is also a nice method for utilization of photocatalysis again. So, and a last moment which I want to note is plasmonic effect. So plasmonic metals, these are metals which are able to efficiently harvest and convert solar energy via localized surface plasmon resonance. Compared with conventional thermal-driven catalysis, plasmonic catalysis can significantly decrease the reaction temperature to achieve desired catalytic activity. Besides, plasmonic catalysis is also able to surmount the equilibrium limits of thermocatalytic reactions. More importantly, performing photocatalytic reactions at mild reactions condition also benefits excellent stability and high selectivity for target products. As a new family of photocatalysts, plasmonic metals serve as competitive candidates for the next generation of efficient catalysts in industry. Localized surface plasmon resonance refers to the collective oscillations of conductive electrons in the resonance with an incident electromagnetic wave. These conduction electrons collectively behave as a coherent electron cloud, and the resonance occurs when the incident light wave with the frequencies is matching the frequency of the electrons cloud of the plasmonic metals. The displacement of the electrons cloud under the effect of external field inducing the creation of charges on the surface. Negative where the electrons are concentrated and positive where we have the lack of electrons. That's why this resonance is coined with the surface effect, while the resonance actually results from the collective oscillations of all conduction electrons in the metallic nanostructures. This resonance is capable of inducing especially inhomogeneous electromagnetic field, abundant energetic charge carriers, and photothermal effect, which is beneficial for many applications such as photocatalysis, surface enhanced Raman spectroscopy, solar cells, photothermal therapy, etc. So, in plasmonic metals, the adsorption of phonons inducing the excitation of electrons, which leads to the formation of two types of charge carriers, that is, electrons and holes. These are hot charge carriers. They generally refer to carriers with energies higher than those of thermal excitation and ambient temperatures. Besides, the relaxation of excited charge carriers further results in local heating, which is also able to serve as driving force for chemical transformation. So at the end, I would like to say that smart responsive materials are usually synthetically prepared. Their properties can be tailored in order to make them responsive for various stimulus. These properties can be used in water treatment application, and so we showed that, for example, atomic layer deposition coating can benefit more efficiency of catalyst under UV light radiation. So almost 100% of methyl orange removal was observed in 1 hour of the process, while for pure titanium dioxide, it was only 72 for the same conditions. The efficiency of piezocatalysis and piezophotocatalysis for nanofiber membrane in our case was 30% more. Furthermore, such catalyst was shown to have a good stability after several successive cycles of photocatalysis. These smart materials are more cost-effective. They could provide higher performance of water treatment. They also can be used for detection of water contamination. And using of these smart materials is a new road and even new dimension in the environmental science. So thank you very much for your attention. It's all from me.
Thank you very much for your interesting presentation. And we have time for questions. Any questions? I have a short curiosity regarding the ALD process of, let's say, deposition and infiltration of the titania tubes. Which is the typical thickness of the ALD process? And can you spend some words regarding the properties of the deposited material? Crystalline, amorphous, depending on the also on the vacuum you are using and also the thickness.
When we obtain the coating by atomic layer deposition immediately after process, the coating is amorphous, and then we annealed it, and we make the structure by following way. It was titanium dioxide tubes which we obtained by anodic oxidation.
Sure.
Then we deposit bismuth ferrite, and then we add the titanium precursor. So it was layered: titanium oxide, bismuth containing layer, titanium and bismuth containing layer. But initial substrate was titanium dioxide nanotubes to give this nice pattern with more surface area. But thickness can be controlled. In our case, it was about 20 nanometers.
Okay.
It was defined by amount of cycles which we produced,
Sure.
and of course we process it by annealing, because the reaction in atomic layer deposition is self-limited. That's why we can obtain these layered structures very
Sure.
well controlled.
So you get some crystallinity with the annealing.
With heating, of course, yeah.
Yeah, okay. Thank you very much. Other questions from the audience? If not, we thanks again Dinara and also the first speaker, Jan Henrik Smat, for their nice presentation. And thank you very much, both. And the video will be available on the Netpore website soon. Thank you very much. Bye-bye.
Bye-bye.
Thank you. Bye.